Section 6.5 is about combining probabilities. This is probably the hardest section in this chapter. Um, we do have a worksheet I've posted about it. That's going to be your chapter 6 and or probabilities worksheet. So please do make sure that you complete that and take a look at that. So here are our learning objectives. Example 1, we're going to talk about and probabilities. So let's suppose we toss 2 fair dice. What is the probability that both will come up 4? Well, oops. Well, let's remember that the odds of me getting 2 4s, right? If we were to roll 2 die, the total number of possible outcomes is 36, right? So the odds of getting 2 4s would be 136. That is the probability of rolling a 4 with 1 die and times the probability of rolling a 4 with another die. What we did was we multiplied, we didn't know it, we're going to see the equation for it, but if you multiply the probability of rolling a 4 with 1 die times the probability of rolling a 4 with another die, that'll give you the probability of rolling 2 4s. This is an example of an and probability. And means that both things occur. So when 2 events are independent, so for example, me rolling a dice and then me rolling another dice, those 2 events don't affect each other. The outcome of one event doesn't affect the other, like I said. Then if I have 2 independent events with different probabilities, the probability that they both occur together is the probability of the first event occurring times the probability of the second event occurring. And this principle can be extended to any number of independent events. The key takeaway is this is and for independent events. So let's say we toss 3 fair coins. What's the probability of getting 3 tails? Well, we know there's only one way to get 3 tails, right? We've done this example a lot before. We've got tails, 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 heads, tails, heads, tails, tails, heads, tails, heads, tails, heads, tails, tails, heads, heads, tails, heads, tails, heads, tail, heads, heads, right? These are the 8 possible outcomes. Well, I can see here that the odds are 1 out of 8, but what if we could have done that a little more simply? Especially if we had 6 or 7 coins that we were flipping, this could be really helpful. So what's the probability of getting 3 tails? Well, that's going to be the probability of getting 1 tail times the probability of getting 1 tail times the probability of getting 1 tail. That is 1/2 times a half times a half, which is 1/8. So when we multiply fractions, we multiply our numerators, that's the top part, and we multiply our denominators, that's the bottom part. Let's talk about and probabilities for dependent events. Dependent events rely on each other. So let's say I have a batch of 15 memory cards and 5 of those cards are defective. I don't know what makes them defective, but 5 are defective. So what's the probability of getting a defective card on both the first and second selection without replacement? That means if I have a stack of 15 cards, I draw one, I keep it, I don't give it back, and then I draw a second one. That's without replacement. Well, the probability of getting my first defect card would be 5 out of 15 because there are 5 defect cards out of my 15 cards. But after that, I don't have 5 defect cards anymore, or, and I don't have 15 memory cards. If I take one card, I've got 14 left, and if I took one of the memory cards, that would mean I have 4 left. So I'm going to get 20 over 15 times 10 is 150, plus 4 times 15 is 60, 210. Did I do that right? We can check it real quick. I always try and get the math worked out in advance, and then I always forget something. Yeah, it's 210. Woohoo! My multiplication skills are intact. So that would be the probability of getting a defect card on both the first and second drawing without replacement, and we might want to simplify that to 2 out of 21 by pulling out a factor of 10. Remember, we always like to simplify our fractions. So if I have and for dependent events, the probability of A and B is the probability of A times the probability of B given A, right? These events are dependent if the outcome of one event affects the probability of the other event. If I hadn't first drawn a defective card, and I kept it, right? That still affects the probability of the next effective card. A way to fix whether or not those events were dependent in order to make them independent would be to put the card back in the deck. But that's not what the way this problem was set up. And again, this principle can be extended to any number of individual events. So let's say a pollsters organization has a list of 1,000 people for a telephone survey, and they know that 433 people out of the 1,000 people they're polling are members of the Democratic Party. Assuming that a person cannot be called more than once, i.e. they're dependent on each other, what's the probability the first two people called will be members of the Democratic Party? So the probability of calling two Democrats, well, first I've got 433 out of 1,000. But then after that, if I called a Democrat, how many Democrats do I have left? Well, I have one left, one less left, which is 432, out of 999 people left to survey because they cannot be called more than once. That's going to give me 187,056 out of 9,999. 999,999. Oof, it's been a long day, gang. That gives me about 0.187 for our probability that the first two people called would be Democrats. Let's talk about either or probabilities. First, we're going to talk about non-overlapping events, where and is when both events occur. Either or is one or the other event occurs. Let's say I want to know the probability of getting heads or tails. Well, the probability of getting heads is a half. The probability of getting tails is a half, and we're going to say I only flipped one coin in this case. So that would be 1, which is 100%, right? If I flip a coin and I want to know what's the probability that I get heads or tails, like either or, it's going to be 100%. So when two events are non-overlapping, they cannot occur at the same time, right? I can't flip a heads and I can't flip a tails at the same time. So if A and B are non-overlapping events and it's an either or probability, then I just add the probability they occur. So the probability of A or B equals the probability of A plus the probability of B. And again, this can be extended to any number of non-overlapping events. So let's say we roll a single die. What's the probability of getting an even number? Well, what are the even numbers on a dice? So the even numbers are 2, 4, and 6. Well, the probability of getting a 2 plus the probability of getting a 4 plus the probability of getting a 6 would add up to the probability that my dice roll is even. So that would be 1, 6 plus 1, 6 plus 1, 6, which gives us 3, 6, which is a half. That's the probability of rolling an even number. And you might have been able to tell me that right from the get-go. Hey, Miss Miller, there are 3 even numbers. That's 3 out of 6 possible options. It'd be a half. But I wanted to make sure we did an or example. Next, we're going to talk about the probability for overlapping events. Two events, A and B, are overlapping if they can occur at the same time. So, for example, if we wanted to look at a group of students who were women or were biology majors, a student could be both a woman and a biology major. So The probability that either A or B occurs for overlapping events would be the probability of A plus the probability of B plus the probability that they overlap, because we're double counting people. And you're going to see that really clearly in this next example, so have a little bit of patience. But that last term, P of A and B, corrects for the double counting of events in which A and B occur together. So let's go through example 6. To improve tourism between France and the United States, the two governments form a committee consisting of 20 people. There are 2 American men, 4 French men, 6 American women, and 8 French women. If you were to meet one of these people at random, what is the probability that the person would be either a woman or a French person? So I want the probability of woman or French. Well, first off, it's always helpful to know what's the probability of them being a woman. Well, I've got 6 men, 14 women, 8 of them American, 12 of them are French. And I've got a committee of 20 people. So the probability of being a woman plus the probability of being French minus the probability of being a woman and French. Well, the probability of being a woman, there are 14 women out of 20. The probability of being French, there are 12 French delegates out of the 20. See how this would add up if I was to stop here and take 14 plus 12, 14 20ths plus 12 20ths, I'd get 26 20ths, which is greater than 100%, which we don't do in probability, right? Probabilities have to be between 0 and 100%, not anymore, so be careful. That's why we can check our work, and we have to account for the overlap. Well, the probability that you're a woman and French would be where the columns woman and French intersect. That'd be right here. So we subtract 8 out of 20. That would give me a probability of 18 20ths, right? And that makes sense because the only people who aren't women or French would be these 2 men, which is 9/10 or 90%. Here is a table that's a summary of all the formulas we've used in combining probabilities. In case you wanted to have them all in one place, this is also table 6.11 in our textbook.